All right, let's talk about precalculus, specifically those two graphs that can be a real headache, secant and cosecant. Now, if you're thinking you have to memorize them, I've got great news. Forget that. We're going to show you a way to build these graphs step by step, using something you already know like the back of your hand. You know that feeling, right? You finally get comfortable with sine and cosine, you're feeling good, and bam, your textbook just drops these two weird, kind of broken-looking graphs on you, secant and cosecant. And the expectation is you're just supposed to, stare at them until they're burned into your brain? Yeah, it's a lot. But what if I told you there's a better way? A way where you don't have to memorize anything new. Seriously. The key to cracking these graphs? It's already in your math toolkit. So let's dig in and find a much smarter way to do this. So here's our game plan. First, we'll talk about why just memorizing is a bad idea. Then we'll show you how to build on what you already know. After that, we'll get to the fun part, the kissing parabolas method. We'll try it out with some examples, and then I'll show you why this is basically a new math superpower. Okay, first up, the memorization problem. Look, trying to just brute force these graphs into your brain, it's not just tough, it's a terrible strategy. Why? Because you're going to forget it the second you walk out of the test. Plus, you completely miss out on this really cool, really elegant connection these graphs have to functions you've already mastered. And that leads us right into the foundation of this whole method. See, the entire trick is built on something you've probably already perfected, graphing sine and cosine. That's it! We're not really learning a new topic here. We're just taking that knowledge and using it in a super clever new way. And it all boils down to these two little things, the reciprocal identities. You know these, right? Secant of x is just 1 over cosine of x. Cosecant of x is 1 over sine of x. That's it. These simple facts are literally the entire instruction manual we need. Yeah, and this quote from Baker's math class just says it all perfectly. We don't memorize these graphs. We build them on top of the ones we already know. That's the whole philosophy right there. It's not about cramming more stuff in your brain. It's about understanding the connection and building the graph piece by piece. All right, which brings us to the method itself. And honestly, it has the best name ever, the kissing parabolas method. I know, it sounds a little silly, but trust me, it's the perfect description for what we're about to do visually. So let's break it down. It's just 3 easy steps. Step 1 is ghost the guide. So if you need to graph a secant function, you're going to start by lightly sketching its partner, the cosine function. And if you're graphing cosecant, you guessed it, you sketch a sine function. Think of this as your foundation, your blueprint. Okay, step 2, draw walls. Now let's think for a second. If secant is 1 times over cosine, what happens when cosine is 0? Well, you'd be dividing by 0, and we all know you can't do that, right? It's undefined. And on a graph, undefined is just a fancy word for a vertical asymptote. So here's what you do. Everywhere your guide graph, your sine or cosine, hits that x-axis, you draw a vertical line, a wall, that your new graph is never, ever allowed to cross. And now for step 3, the best part. Kiss the peaks. This is where it all comes together. You go to every maximum point, every high point on your guide graph, and you draw a little U shape that just barely kisses that peak and then flies up towards those walls you drew. Then you do the opposite for the minimums, the valleys. You draw an upside-down U that kisses the bottom and shoots down. And that, right there, is why we call them kissing parabolas. Okay, so the theory sounds good, right? But let's see it in action with some actual problems. It's time to put this thing to the test. So, for our first example, how do we graph y equals 2 secant of x? Well, what's the first step? We got to find its reciprocal partner, right? All right, let's do this. Step 1, ghost the guide. The partner of 2 secant x is 2 cosine x. So we sketch a nice cosine wave that goes up to 2 and down to -2. Easy. Step 2, draw the walls. So where does that cosine graph hit 0? At pi over 2, 3 pi over 2, you know the drill. That's where we pop in our vertical asymptotes. And finally, step 3, kiss the peaks. The high points of our guide are at y equals 2. So we draw our little parabolas kissing those points and going up. The low points, the valleys, are at y equals -2. So we draw the upside down parabolas kissing them and going down. And boom, you're done. You just graphed the whole thing and you didn't have to memorize a single shape. Okay, cool. Let's switch it up a bit. For this next one, we don't even need the whole graph. We just need to find the vertical asymptotes of y equals cosecant of 2x minus pi. So let's think. The asymptotes, the walls, happen wherever the guide function is 0. The guide for cosecant is sine, right? So we just need to figure out where sine of 2x minus pi equals 0. Well, just think about a normal sine wave. When is it 0? It's 0, at pi, at 2 pi, at negative pi, basically at any whole number times pi. So we can just write that as n pi. Now all we do is set the stuff inside the parentheses equal to that. So 2x minus pi equals n pi. From here, it's just a little algebra. Add pi to both sides, then divide everything by 2, and there you have it. That's the formula for every single one of the asymptotes.
All right, ready for a challenge? Let's tackle an advanced one. Y equals negative secant of x plus 1. This one's got a flip and a shift, which is where things can get a little tricky.
So, first things first, we ghost our guide, y equals negative cosine of x plus 1. So that's just a normal cosine wave that's been flipped upside down and then moved up 1 unit. Now, listen up, because here is the most important part of this whole problem. Where do the walls go? Your first instinct might be to draw them wherever this new shifted guide hits the x-axis. But that is the classic mistake. Don't do it. Remember why the walls exist in the first place. They're where the original cosine function is 0. That plus 1 shift doesn't change where the original function was 0. So the walls, the asymptotes, they stay in the exact same place as they would for a regular secant graph. Once you've got those walls in the right place, then you go ahead and kiss the peaks and valleys of your new shifted guide.
Okay, let's zoom out for a minute. You might think you just learned a neat trick for graphing, but it's actually way, way bigger than that. You've just unlocked a whole new way of thinking about tough problems.
Think about what we did. We used a simple, familiar guide function, our good old friends sine and cosine, to build and totally understand a much more complicated graph. This whole idea, using a simple thing to figure out a hard thing, it is one of the most powerful tools you will ever use in math.
And I'm not just talking about precalculus. When you get to calculus, this mental model is absolutely essential. You're going to learn about things like the squeeze theorem, which sounds intense, but it's literally this exact idea. You take a super messy, complicated function and you trap it between two simpler ones to figure it out. It's all about using what you know to tackle what you don't. So, what you picked up today? This is setting you up for success down the road.
And that brings me to my final thought, which goes way beyond the classroom. This whole guide function idea, it isn't just for math. Think about it. In coding, in engineering, really in any kind of big, messy problem solving, this strategy is everything. So I'll leave you with this to chew on. What other complex problems in your life could you solve if you just started by understanding a simpler related one first?